Today we're going to talk about electric fields and field lines. We're going to define what the electric field is, and here's basically mathematically how we define the electric field. And then we're going to talk about electric fields for point charges, and then we'll talk about uniform electric fields and how to solve problems with those. Then we're going to talk about how to draw electric field lines. There are 5 rules that I'm going to give you for drawing electric field lines, and then we'll work a couple of examples. But first, let's review Coulomb's law, which is given by this equation. And so we'll talk about Coulomb's law real quick. We said that, matter is made out of charged particles. We have protons, which have positive charge. We just arbitrarily call it positive charge. Electrons carry the negative charge. Of course, there's other things like neutrons. They don't have any charge at all, any electric charge anyway. And then, of course, there are other particles that exist, and there's dark matter and all that stuff, but we're not going to worry about that. We're just going to talk about these things. And if I have a net positive charge and another net positive charge, they could be, whatever, they're going to push each other apart. They're going to repel. Like charges repel. And of course, it's Coulomb's law that tells us what that force is. Coulomb's law is equal to the electric constant times, we're going to call this charge 1. And it's directly, the electric force of repulsion is equal to, it's proportional to Q1. It's proportional to Q2. And also the distance between them, which we're going to call R squared. And now it has a direction, and I'm going to call that direction R hat. And I think we dealt with this before, but R hat just means away from. So K Q1 Q2 over R squared in the R hat direction, that just means it's a repulsive force. And if it's negative, if one of these charges is negative and the other's positive, you get an attractive force, and that means it would be in the negative R hat direction. That just means it's attractive. And you worked some problems involving that on the last assignment. Okay, so now we're going to get into electric fields. Now, what is a field? A field, or a force field especially, a force field is a region of space where if you are in that space and you have a certain characteristic, you're going to feel a force. For example, gravity fields. Like, let's talk about gravity fields for a second. So here's the surface of a planet. Okay, it could be Earth or whatever. And here's a satellite or a meteor or something out there, some massive object. It feels an attractive force towards that planet. And that attractive force is because there is a force field around that planet. And it's because this object has mass. So even though if I put the mass over here, if it's in the region of space around this planet, it's going to feel a force because it's in that region of space that's being influenced by the planet. And that's a gravity field, okay? And of course, we have an equation for the force of the gravity field. The force of gravity equals m times g. And then we can, of course, use Newton's law of gravity. But what if I say g equals the force of gravity per unit mass? This right here is a gravity field. It tells us how much force we're going to get because we have a certain amount of mass. So that's newtons of force per kilogram of mass, right? And at the Earth's surface, we know what that gravity field is, right? It's 9.8 newtons of force per kilogram of mass. Okay? Now, electric fields work the same way. But instead of the characteristic being mass, it's charge that we care about. Okay, so let me show an example of an electric field over here. What if I've got a sphere, like a metal sphere or something, and I'm going to put charge all over this sphere? Well, we know that positive charges repel. Let's say these positive charges are fixed in place. They're not allowed to move. They're going to stay right where they're at. But let's say I put a little positive charge right here, right? It's going to be repelled by these charges here. So it's going to feel an electric force. Now we can use Coulomb's law to figure out what that force is. And we didn't really talk about this, but all of these, well, I won't get into it. We can figure out what the electric force is for point charges anyway. But this thing has charge right here. This little guy right here that I'm just going to pick up and put in space somewhere. I'm going to call this charge that I'm going to test the electric field with, I'm going to call that Q naught. Okay, this is Q naught. And Q naught is also sometimes called a test charge. And I use this charge right here to see what the field is like around these charges right here. Okay? And so now, so I'm gonna put it right here. Well, let's just put it right here. So this feels a certain force, and I've got a certain charge on it, Q naught. Now I define the electric field at this position right here. The electric field, and I'm going to call it E with a vector hat. Now I know we've used the capital E before for mechanical energy. Sorry, now we're going to use capital E to represent the electric field. And by definition, the electric field is equal to the charge, to the force at this location in space. The electric force at this location in space divided by my test charge. Okay, so it's how much force I get per unit charge right there. And it has units of newtons of force per coulomb of charge. Now here's something really, really important to understand. This test charge is a charge over here, not the charge on this sphere. Okay? It's the charge of my test charge. Well, now let's figure out what the electric field is for a point charge. So let's put a point charge right here. And let's say, we'll go ahead and use some values here. Let's say Q is equal to 10 microcoulombs. Oh, I better zoom out or I'm going to get off screen. Now, let's put my test charge here, Q naught. Now, I can give Q naught any value of charge I want. I'm not going to give it one. I'm just going to say, well, I will. Yeah, let's go ahead and give it a try. I'll say my test charge in this case is 1 microcoulomb because it makes the math easy. All right. And let's say that these guys are 2.0 meters apart. So that's the distance. So I can figure out what the force is on this guy right here. The force on that guy is equal, the electric force, on this guy. Well, first of all, I could tell the direction. It's going to be away from this. And it's going to be K, Q naught over R squared, right? That's Coulomb's law. And the direction is away from, positive R hat, away from. So let's plug in our values now. This is 9 times 10 to the 9 Newton meter squared per Coulomb squared, right? That's the electric constant. And then what is Q? Q is 10 microcoulombs. Q naught is 1 microcoulomb divided by r squared. What is the distance between these? This is 2 meters. And we're going to square it. So now let's figure out what that electric force is. Get my calculator out. Are you done with those three?
Yeah.
Okay. All right, we'll do the other three. Okay, so here we have 9, or you can put 8.99 as the actual value in the thing. Yeah, that's fine. 9 times 10 to the 9 times. Now, here, look at this shortcut right here. This is 10 microcoulombs, so I'm going to go times 10 to the negative 6. Don't forget that micro means times 10 to the negative 6. If you forget it, you'll only be off by a factor of 1,000,000. So don't do that. Times 1 times 10 to the negative 6 equals, and then I'm going to divide it by 2 squared, which I could have just put as 4, right? And you get a pretty small force, 0.0225 newtons. So that's how much force Q naught feels, the repulsive force, this many newtons. Now, but what is the electric field right here? Well, the electric field right there is equal to the electric force divided by Q naught. So this is going to be 0.0225 newtons divided by Q naught, which is 1 microcoulomb. And you got to remember to divide by that micro. Right? Oh, it's just 1. No, it's not just 0.0225 newtons per coulomb. You got that micro in there. So let's do the math. So it's 0.0225 newton divided by 1 times 10 to the negative 6. Negative 6 micro, negative 6. Thank you. Equals, and I get a big number here. This is 22,500 newtons per coulomb. So it's actually a really strong field. In other words, if I put a coulomb of charge right here, I would feel 22,500 newtons of force. Okay, so this is the definition of electric fields. You can, of course, apply it to. Now here I worked a concrete problem, but really, for a point charge, if I have Q right here, and I have Q naught over here, I can say, well, the electric force is equal to Q naught over R squared, but I want the electric field. So I have to divide by Q naught. So this is why it doesn't matter what Q naught is, because look, it cancels out. And so I can say the electric field for a point charge is equal to KQ over R squared in the away from direction. Now, you know when you make your, when we make an equation list, right? So this is going to be in your equation list, and I tell you to like sometimes put comments in there or restrictions. This is for point charges only. Okay, so don't use this equation if I give you a different kind of electric field. Now, sometimes we're going to deal with uniform electric fields. And I'll show you how we do that. Here's what we do. we take a plate of metal and we put charge on it, positive charge. Then we get another plate and we put an equal amount of negative charge on it. Now, if these plates are big enough, then and they're close together enough, what we get are electric field lines, between the positive and negative charge. Oh, I haven't talked about field lines yet, but and we'll talk about electric field lines in a minute. But we're going to get a field in between those plates where the field is constant. A constant field. And so, I'm actually going to teach you how to draw these electric field lines properly here in just a minute. But what we can do is, see, we can represent the electric field as kind of being something like this. And if I put my test charge in here, let's put it right there, it's going to feel a force. The force on that is going to be equal to that. Well, okay, let me start with the definition. The electric field, by definition, is the force on this test charge divided by Q naught. And if the charge is, if the electric field is uniform, that is, no matter where I am, it's in the same direction and it has the same value, then this little test charge is always going to feel a force to the right. Okay? So if I want the force on my test charge, the electric force on my test charge, then I just take the charge and multiply it by the field. And now, what if this is the net force acting? If this is the net force acting on that charged particle, that's going to be equal to ma. And the acceleration will be in the same direction as the electric field. And so you can solve for the acceleration. Take the charge of your particle, multiply that by the electric field, divide it by the mass. Now, what if this is like an one thing. What if I put a charge in here that's like an electron? Well, it has a negative charge. So when I put a negative in there, that just means that the force on it is going to be in the opposite direction. So what do electric fields do? If you have an electric field, here's what it does. Let me write this up here. What do electric fields do? Electric fields apply forces to charged particles. Okay, that's what electric fields do. They apply forces to charged particles. So if I have in some region of space, if I have some region of space, I put a charged particle in there, it's going to feel a force. And the force, the direction of the force, is determined by the direction of the electric field. And the magnitude of the force depends on how much charge, right? How much charge I have, and how strong the electric field is. Okay. Now, let me zoom out. That will kind of review. All right, so now I got a little ahead of myself because I started drawing electric field lines. So let's do that. Let's talk about electric field lines. Electric field lines don't really exist in nature. They are constructs in our imagination that allow us to visualize what's going around in the space around an isolated charge. So let's put a point charge right here. Let's put a big clump of charge right here. It's got a certain amount of charge, Q. Now I'm going to put my test charge right here, little positive test charge. I'm a little test charge, short and stout. So this is going to feel a force. But what if I, so here's the force that it feels. Or actually, you could think of this. This is actually the electric field when I divide by the force by this Q naught. Well, what if I put Q naught over here? Well, now I'm farther away, so it's not going to be as strong, but it's going to be in the same direction. Well, what if I put it here? It's going to be a little weaker, but no matter where I go, see, I can just keep lining it up. And so what I'm going to do is I'm going to draw an electric field line. This is my field line. Well, what if I started here instead? What if I started here instead? What if I started here instead? See how it's pushing it away? What if I start here instead? Oh, it's pushing it away. So I get this nice symmetric pattern of electric field lines away from my charge Q. Now, one of the things you notice is that how many field lines you draw, it's kind of arbitrary. You just want to draw enough to visualize the space around it. But where do these field lines end? Well, look, the universe is electrically neutral. So that means there's just as much positive charge in the universe as there is negative charge in the universe. There's just as many protons as there are electrons. Yay. So that means that if I isolated all this positive charge, that means there's some very unhappy negative charge out there. And what we're going to do is we're going to pretend like it's evenly distributed throughout the universe. And that's where the field lines end. What if I put negative charge right here? Now, this is a completely separate problem. What if I put a clump of negative charge right here? Well, if I put my positive test charge here, it's going to be attracted. Attracted, attracted. So the field line is going to look like this, depending on where I start. Oops, that was terrible. This one is terrible, terrible field line. Okay. So field lines, so here's one thing about field lines. They start at positive charge, and they terminate at negative charge. Draw it as an arrow. It starts and ends, right, like that. Okay, so now there are some rules for drawing field lines. Okay, rules. These are the rules. They start at positive charge. All electric field lines, when you draw it, they start at positive charge. They end at negative charge. Also, when you draw an electric field line, when you draw a bunch of electric field lines, the number of field lines is proportional to the amount of charge. I'm going to do an example of that here in a bit. You also want to you want to draw enough field lines to visualize the space. I mean, there might be a situation where I give you 2 point charges and you can describe it out. You can put in like one field line, but one field line doesn't describe the space. So you want enough. You want enough field lines. It's kind of arbitrary, but you'll know it when you see it. And here's another rule. Never cross field lines. Okay, there's a great old movie in the early 80s called Ghostbusters. And there was one rule they had. Never cross the stream. If you cross the streams, every atom in your body will explode at the speed of light. Well, if I ask you to draw some field lines and you cross field lines, 3 points from your exam score will explode at the speed of light, never to be seen again. So let me show you just some real quick examples. I'm running out of time, so I got to do this quick. What if I have 5 microcoulombs of positive charge here. 1, 2, 3, 4, 5. And you don't have to draw 5 pluses for 5 microcoulombs. It's totally arbitrary. And let's suppose over here, I've got 1, 2, 3 microcoulombs of negative charge. What's the field going to look like? Well, just pick somewhere. And I'm going to go here. And if my positive test charge is going to be repelled here and attracted to here, but you kind of do this. And then the closer my test charge, here's my test charge. Oh, now it starts feeling, and it gets attracted and terminates at that negative charge. And then maybe I'll do the same thing over here. Boom. And then maybe I'll draw one out, goes out like this. Now, see, there's more positive than negative charge, so it kind of dominates. Pushes me away, pushes me away. Oh, wait, but now I'm being attracted. Now I'm being attracted and pushed by the positive. No. Boom. Like that. Now, I got to make this proportional. This is 5 and this is 3. 1, 2, 3, 4. I'm going to have to put in a lot more lines. 1, 2, 3, 4. See, 10. Yeah. So, went off the paper and then back in like this. Now, here's the deal. I put in 1, 2, 3, 4, 5, 6 field lines into here. If I put, now listen. If I put 6 field lines into this negative charge, how many field lines have to come out of the positive charge? If the number of field lines is proportional to the amount of charge. Well, I doubled 3, so that gives me 6. So I got to double this. So I have 1, 2, 3, 4, 5, 6. So I need 7, 8, 9, 10, right? If I have 6 coming in here, I have to have 10 coming out here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, where do these end up? Where do these go? Well, the universe is electrically neutral. So somewhere way out in space is some negative charge. We're going to just pretend like it's infinitely far away. So look, field lines, they did. I started at positive and I ended at negative. So you got to put the arrows on here on these field lines because that tells you the direction that your test charge is being pushed in. So they start at positive, they end at negative, and it's proportional. If I have 6 lines coming into negative 3 microcoulombs, I have to have 10 field lines coming out of the 5 because I've just doubled the numbers, see? I have to have enough to visualize space. This is kind of enough. And I didn't cross any field lines. What would happen if I crossed a field line? Well, that's like saying this. Okay, don't even put this in your notes. Just watch. What if I have a field line that goes like this? Well, that means that if I put my test charge right here, it feels an electrical force in this direction, a net electrical force in this direction, and a net electrical force in this direction. That can't happen. You can only be pushed in one net direction at a time. This makes no sense. Don't do it. Bad. Okay? So follow these rules. Just practice them a little bit, and when we get back, when we get back together, we will discuss this. And so that, I think we've covered everything on this list, and my phone is ringing. Isn't that lovely? So that is all.